Okay, let's get going. Going to talk through a lot of stuff here, kind of just like Zora was describing last time, a carpet sweep of some big ideas. Some of this topic, water and water resources, we've explored already just a little. We back when we talked about climate and weather and sort of water availability in a general sense. We learned about groundwater and aquifers and such. So some of that, that's all in this same chapter. We're kind of expanding on it now. So we'll start here, though. You've seen this picture. It's from your book. I'm going to pose a question slightly different. We know at this point that rain doesn't fall equally across the surface of the earth. Some parts are just drier than others. Obvious examples would be the big deserts. The Sahara is there. The Kalahari down here, southern Africa. The southwestern United States. Mojave and the Sonoran deserts. Australia, for example. Most of Australia, much of Australia. Just dry places. It doesn't rain that much. Why? There's a lot of clues on there, yeah.
Latitude.
Okay, so latitude, distance from the equator. The equator goes just about right there or so. The tropics, the heart of the tropics there, right around the equator. The most rainfall, right? The wettest place, the warmest, wettest. If we go just outside the tropics, or just on the edges of the tropics, we hit these bands of what we call these high pressure belts, these areas where it doesn't rain as much. All of the rain fell in the tropics. Air in these parts of the world, I'm just going to use Africa as my example, is now dry and sinking back down towards the surface, very little rainfall. What other factors would contribute to less rainfall one place compared to the other? That's really brave. Why do you suppose I put up a picture with ocean currents on it? Because the ocean currents matter. Yeah. Cold water currents. So down here, once again, southern Africa, western South America, western U.S. The cold water currents don't evaporate as much, put less moisture in the air. What's also true is they act as a surface for water to condense, these cold oceans. So they actually have a drying effect on the air mass above them. One more reason why we might end up with less rainfall one place compared to the other. Now, if you layer that kind of natural inequitable distribution over the fact that we have these growing populations in many parts of the world where water is already scarce, well, then we have an issue. And much like we've been talking about with other issues in this unit, the solutions are going to lie in people's values and the decisions they make, as well as government's role in regulating and kind of managing, as well as market's role in kind of determining what it's worth to people and what kind of investment they're willing to make. I'm going to show you, let this video play here. Just an animated thing, narrated, talks through. I'll let that go as kind of an introduction, and then I will expand on many of these ideas with some pictures and stuff after. So, here we go.
seem surprising. After all, on average, people only drink about 2 liters of water a day. But water plays a big role in our daily lives. And in that same 24 hours, most people will actually consume an estimated 3,000 liters of water. In fact, household water, which we use to drink, cook, and clean, accounts for only 3.6% of humanity's water consumption. Another 4.4% goes to the wide range of factories which make the products we buy each day. But the remaining 92% of our water consumption is spent on a single industry. All farms drain the equivalent of 3.3 billion Olympic-sized swimming pools every year. All of it swallowed up by crops and livestock to feed Earth's growing population. Agriculture currently covers 37% of Earth's land area, posing the biggest threat to our regional water supplies. And yet, it's also a necessity. So how do we limit agriculture's thirst while still feeding those who rely on it? Farmers are already finding ingenious ways to reduce their impact, like using special irrigation techniques to grow more crop per drop and breeding new crops that are less thirsty. Other industries are following suit, adopting production processes that reuse and recycle water. On a personal level, reducing food waste is the first step to reducing water use, since 1/3 of the food that leaves farms is currently wasted or thrown away. You might also want to consider eating less water-intensive foods like shelled nuts and red meat. Adopting a vegetarian lifestyle could reduce up to 1/3 of your water footprint. Our planet may never run out of water, but it doesn't have to for individuals to go thirsty. Solving this local problem requires a global solution, and small day-to-day decisions can affect reservoirs around the world.
Okay, I'm going to stop it there. It goes on to implore you to participate in their student things. So we'll stop there. All right. I put in, I meant to mention this before. There are some of these slides, like you've seen this one before. I've actually done this math before. I put in a couple of slides that I've shown you before, not because I'm going to talk through them again, but I wanted them all to be for review, and you can kind of see how it all fits together. So anyway, let's see. So the animated video thing there just through this question of how much is around, how much fresh water do we have, how much is accessible to us. It's actually a very small. We also know that it's not distributed equally. So the question becomes, in a changing climate with these growing populations, can we get enough water to where the people are? And I'm going to talk through some examples of how exactly we do that, because we've done that for a long time. We've invested a lot of time and money and energy into figuring that out, and we are quite good at it, I might say. Anyway, groundwater. These are slides, like I said, I've shown before. A lot of that fresh water resides in the ground as groundwater. There's the Ogallala Aquifer. Here, we're going to talk mostly about surface water. And some large-scale efforts to divert it to where we need it. Or keep it where we need it, I should say. So the biggest and perhaps most obvious way we do that is that we build dams. A dam stops the flow of a river. Okay? And therefore, the water backs up behind the dam, and it creates a reservoir, shown there. That reservoir is called Lake Kootenai. It's in Montana. This is the Libby Dam in Libby, Montana. And that is a really kind of classic prototype of a hydroelectric dam. It's a dam that generates electricity. The river, the moving water, is running into the dam, and it's coming up into the reservoir. What's happening in the dam, kind of under, is the water is being channeled into these narrow tubes, water moving at a high rate, moving over a turbine, which is being forced to spin by the moving water, and creating electricity. And that, in a nutshell, and that's a big reason to want to build a dam. And I talked about, not so long ago, talking about land use, this example of Hetch Hetchy and in Yosemite National Park. The Yosemite River, the Tuolumne River, I believe the Tuolumne River, was dammed in 1913 because San Francisco, which was not too far away, was rapidly growing and rapidly clean water supplies. So what do? We stop the river and we create a reservoir, and now we have a nice stored water supply, reliable chunk of water right where we need it, right where we can manage it. In addition, we get this hydroelectric benefit, electricity generation. So do talk about energy. Big question is going to be about renewable versus non-renewable, clean versus dirty, all these ways to describe energy. Well, hydroelectric energy is clean and renewable. It comes at a big cost to habitat and such, but it is zero carbon, right? There's no carbon emissions. It's one of the cleaner, more renewable ones. So. What's also true is in the United States, we have dammed pretty much all the rivers we can dam. In fact, we've come to a point in this country where we are removing dams because we no longer need them. Not dams like that, but more dams like this. Smaller ones built more for purposes or for flood control. And now in parts of the world, for example, in the western U.S., where perhaps agriculture never developed in the way that it was planned for, or perhaps that area is no longer used to grow crops and it's reforested. There's a lot of reasons why we remove dams that have kind of outlived their usefulness, but that's actually happening. One of the reasons is that sediment can build up behind them and affect the ecosystem. But it's just kind of an interesting thing. Dam removal is interesting. It's something we could talk a lot about, but we're not going to right now. Other consequences of building dams down here. I mentioned sediment. Rivers, I put this picture here to illustrate this. That's the, what is that? The Yuha River, I believe it is, in like the Pacific Northwest. And you can see all that sediment moving downstream. Rivers carry sediments, and that sediment is the foundation for a lot of systems that occur downstream. It's nutrients, it's substrate, it's a lot of things. It's important, and that sediment is being dammed up with the river in a lot of cases. Now, there are ways to manage that. Build in ways to kind of manage it, but sedimentation is something that happens over time if you're going to have a dam, and it's a problem. It's a problem for the reservoir. It's also a problem for downstream habitats, depriving them of nutrient and so on. What's also true is that the floods that are being prevented by the dams are kind of a necessary component of the natural system downstream. Remember that intermediate disturbances are good for biodiversity. A lot of species depend on that. It's also really kind of foundational, flooding is, to moving around nutrients, getting and onto the river banks. That's very supportive to the living system on the river banks. Preventing that, we're altering the system. Okay, we're altering the native functioning of the system. What's also true in terms of biodiversity is that the dam prevents movement of species in the river habitat. So fish that migrate from saltwater to freshwater, like salmon, really significantly impacted by dams like this that exist across the rivers where they should be migrating through. So they build ladders. That's what they're called. That's what this is right here. And it's exactly what it sounds like. It's a spot where the fish can hop up and over and around the dam. And they're apparently pretty effective. Can be anyway. But dams are it's a question of values, just like everything else we've been talking about recently, or most everything else. What cost are we willing to accept for the benefits? This is, I just thought worth a mention. It's mentioned in your book also. That is the Three Gorges Dam in China. That's the Yangtze River. And it's the biggest in the world. It's the winner. Took a real long time to build. They just finished building it, I don't know, within 10 years from now. I can't remember what year it was. But it's like 2 kilometers long or something. It's just huge. And, billions of dollars in investment and huge impacts to the system and so on. But the outcome is clean, renewable energy, and everything I just mentioned, right? The opportunity to develop land agriculture because we're controlling floods and so on. So we're quite good at building dams, and we have been for a long time. Also real good at building aqueducts. Just ask the Romans. Different now, but it's the same idea. An aqueduct, so a dam is damming a river, bringing the water there instead of letting it flow downstream, and we'll get it when we need it. An aqueduct is bringing the water to us. Okay, New York and Los Angeles are 2 major cities in our country that are almost completely dependent on aqueducts to bring in water from hundreds of miles away. In the case of New York, it's from the Catskill Mountains in the west part near the Canadian. Los Angeles, it's from the Colorado River inland, so east from LA, and also from the Owens River, which is shown here, which is in northern, it's not in northern California. I almost said that's not true. It's near the southern, this is the southern Sierra Nevadas right here. So it's kind of the middle California, northern Mojave Desert, the Owens River, Owens Valley. And in both cases, the water is moving massively. It's going downhill right to the city. So this aqueduct from the Owens Valley goes up and over several hills on its way down to Los Angeles. And it can do that because ultimately the Owens Valley is up here and LA is down here. And the water moves down. Now, in the case of New York, the capital, a lot of impacts to the natural environment as a result of that. But that's a place that kind of rains a lot. You get a lot of snowfall typically. Recharge isn't as much of an issue. But in the Los Angeles example and the example from your next recharge, you're taking water from a place that's already dry. A place it doesn't rain very much. The Owens River is snow melt from the Sierra Nevadas. It's in the desert, but it was accessible, and it's not helpful. But it was accessible, and it was logistically feasible, and it's Los Angeles now. It also this whole question of aqueducts, excuse me, raises a really important question of ownership and water rights. Rivers flow across international boundaries, for example. So if I'm here in the United States saying that the Colorado River is mine, well, then Mexico can't have it. And that's a source of conflict. Okay? In the case of the Owens River, for example, this is a topic that I could talk a lot about also, much like removal. But there were some shady dealings going on there. The city of Los Angeles, and this was years ago, I would say the 20s and 30s. But the city of Los Angeles bought the river first because they couldn't just divert it. They had to own the rights to it. So they went up there and they, in some cases, legitimately bought land and bought. In other cases, they very illegitimately did that. But that's a different topic altogether. End of the day, they bought the river and they diverted it to Los Angeles. Since then, they've built aqueducts out of Colorado and other places too. But going to great extent here to divert water and get it to where we need it. And what are we prioritizing? We're prioritizing these large urban areas, big population centers. Right? Okay, one more way we can do this. 71%, as the video just told us, of the Earth's surface is ocean. And excuse me, wouldn't it be great if we could drink ocean water? In parts of the world, and they're showing this map here, where there is little to no freshwater availability per year, so the Middle East and North Africa. In parts of the world where that's an issue, this has become a pretty popular solution. I'm trying to remember the number now. It's at least 50% or something of the desalination that happens in the world is happening in the Middle East, for example. It is energy technology dependent, but it works. It happens two ways. One is by distillation, the other is by what's called reverse osmosis. If you are distilling something, what you are doing is you are heating it until it evaporates, and then you're collecting the vapor and condensing it. And that's what we do with the salt. We heat the salt water, we collect the fresh water vapor that's left behind, we have drinkable water now. The question there becomes, what do we do with that salt? It's really highly concentrated. It's toxic in the natural environment. What do we do with it? Reverse osmosis is an interesting idea. You can buy reverse osmosis filters to put under your sink and such. I mean, it's technology that's out there and available, and it is actually more efficient than the distillation thing. And what we're doing there is we're forcing water through a really fine filter. We're putting it under pressure, and we're forcing it through these little micropore filters that are filtering out the salt and leaving us with the water. Either way, it makes ocean water accessible to us as fresh water. There is, and there could be other ones we don't know about, but in the United States, there is a desalination plant on the Gulf Coast of Florida. I'm trying to remember where, and I can't. Tampa, St. Pete, maybe. And there's another one on the coast of California down here, the Catalina Islands. So it's something that's happening. A lot of places, but it tends to be, like I said, it tends to be in those places. It tends to be, in some cases, the best option in places where there's very few other options. So how do we make water available to us? A lot of ways. Okay. All of it with some kind of cost to the natural system, or some kind of financial cost as well. Keeping water out. This is my one slide to illustrate that. It tends to be the case that coastal areas and areas along rivers are really highly valued real estate. In the case of the rivers, it's also really highly valued as agricultural land. Along the banks of rivers, you find really fertile, rich soils. Those are the floodplains of the river. And I mentioned already flooding, right? When a river floods, sediments get pulled up onto the bank and left there. And that's nutrient. That's fertile soil that's being developed over time. So we tend to have a lot of farms in these really low-lying areas around rivers. It makes sense from a production standpoint, from a farming standpoint. However, when that river floods, we lose our crops, and that's a huge problem. So, or in the case of New Orleans, after Hurricane Katrina in 2005, which seems like forever ago now, or in the case of St. Louis in 93, when the surfaces are not permeable to water like they are in cities, it's asphalt and concrete, water stays on top, and you have kind of a big problem now. In the case of the fields, like I said, it just crops. It takes a whole year's worth of income out of the farmer's hand in some cases. Yeah. So we want to protect these areas. We need to protect these areas. If we're going to live there and work there, how do we do that? We build levees. Okay. A dike is the same idea, except it's an ocean we're trying to keep out and not a river. This is an example from Norway. This Netherlands, kind of along the northern Europe there. A lot of coastline up there. But But that's the idea, right? If we're going to use these lands for these purposes, we need to protect them from flooding. And this is how we've done that historically. Moving forward, it's going to be interesting because climate is changing, precipitation patterns are changing, sea levels are changing. So a lot that was made years and years ago, it needs to be revisited on some level. Will it still be effective or not is a big question. Okay. Okay. So, this question of conservation. How do we do this? Okay. We got population. We got climate change. We got to feed all these people. We got to water all these plants. How are we going to do this? And it's a question of efficiency, and that's true when we talk about energy. Use by wasting less. The idea. Okay. In terms of, I'm talking about, but in terms of industry and household use, that's a form of technology. A technology that just uses less water. Think of your washing machine, your dishwasher, your toilet. These things are being made more efficient for water use. Toilets now that have you seen these? Right? One's for number one, one's for number two. All right. Less water, more water. All right. Yeah. Of household use also, often it's about incentives, kind of incentivizing using less, offering some kind of perk or benefit if you do certain things or don't do certain things. You can get money, for example, for landscaping that helps to retain water. I'm putting together my grant application right now, actually. That's money being made available through the Deer Creek Watershed Alliance. Governments do the same thing. They'll do it with energy also. Incentives for getting solar panels, incentives for using less water. Or you could think of it the other way, penalties for using too much water. Either way, we're talking about incentivizing someone. In terms of anything, right, developing technology to use less, but also to reuse water and reuse water smartly is kind of another direction we're headed with this efficiency question. So there's a lot going on there, but that's a really small sliver of the total consumption. Most of agriculture, and most of that is related to irrigation. So drip irrigation is the one you read about as being kind of the trendy new way to do it because it is really efficient. And in this case, what we're doing is we're putting hoses right along the ground or maybe under the ground, and water just seeps out of small holes in the hoses. Goes right to the roots. It's not evaporating in the sunlight. It's not running off into the river. It's going directly into the soil, right to the roots, really highly efficient. Requires some investment, though, right? And requires some know-how and some technology. But that's becoming more and more of a thing. We're seeing a lot of places. These other methods of irrigation are used widely, for sure, and they still are, and they still will be. But when comparing them, we want to think in terms of efficiency. Okay, how much runoff and evaporation versus how much getting to the plants and being used. Some of those numbers might be a little, maybe not. I don't know. For spraying, it'd be surprising, but you can do it effectively, and people do. Point my sprinklers here. This picture, they're really small, but there are many forms of spray irrigation. Big ones that drop the water down, for example, instead of bringing it up. So a lot of ways to do it. But either way, we're talking about really intensive water use. Okay, so that, look at the size of these fields. If I'm talking about a 25% change in efficiency, that's a lot of water when we talk about that amount of area. Okay, 37% of all is used for agriculture, right? What if across that whole 35% used to be by 25%? That's huge. Okay, that's a lot of water. All right, so last one. We have some time to go through some of these figures and calculate some things. We will, but this graph, also from your book. Water withdrawals in the United States. Going 1955. That's in billion liters. Kind of an interesting, but that's what it is. And you can see the trend. And if I were to like overlay on the population of the United States in that 50 years, the energy consumption of the United States in that 50 years, right? The United States in that 50 years, right? You can add water into this category of things that over time grow, the consumption of which changes over time as populations grow, as affluence increases, as lifestyles change. Water consumption tends to increase. All right. Why? Not rich people drink more water than poor people, because products, all the other stuff it's about the you flush your toilet, although that matters. Any questions on any of that? Can somebody tell me when this class ends? 4 minutes. That's like 4 more than I thought I had. Okay, so let's see here. Let's spend some time. Let's look at this one. This is a good one. Or one here, we'll use it again. Kind of a lot going on here. Top 10 freshwater consumers. So these are countries. Nigeria is on the list. Interesting. And then over here, that consumption, right? So you can see China's segment of the consumption and how that's broken up by segment. Household versus industry versus agriculture. Excuse me. Yeesh. So that, I guess what I'd say in your interest of time, what the three are I think fairly obvious. Hopefully, it's the top 3: China, India, and the U.S. Rapidly growing populations. Okay, rapidly expanding agriculture. Right, changing lifestyles. China and India. In fact, if you compare the U.S. to most other countries on this list, you got a lot of what we might call developing countries or countries in that phase 2 of the demographic transition. All right, places that we might expect their consumption to increase. We also have places like Pakistan, for example, that are already pretty dry. So we have this compounding issue of population growth. So before you go, I guess if we have like a minute, see if you can figure this middle one out. The total consumption in gallons. These are shown in cubic mil, a dimensional analysis. 800, I forget. Oh, come on, where is it? Total consumption again. So what you would do, okay, hang on. Poorly asked question, sorry. If this is cubic meters, you just add those all up, and then you do your conversion here. That was the idea. But we can save that for another day if you guys want. Questions about water consumption, water availability, resources in general? Okay.